Okay, so thanks for being on time. So what we've seen so far is how we define points and coordinates. This should be familiar, but just to be sure that we all understand the same stuff. And through the semester you will understand why I'm insisting, but hope now bear with me. Okay? So we have points, but we need to start moving them around. Okay? Because robots is all about motion, and we need to see, okay, I have a point, I have coordinate frames, how do I move them around, how do I rotate them, how do I translate them, okay? So we'll define a thing that is called a transformation matrix, okay? I'm going back to 2 dimensions, see it as an example in 2 dimensions, and we're going to go back to 3 dimensions. It's a bit easier to start with 3 dimensions, okay? So we define this transformation matrix. We usually use R or T, capital. And usually for R we define about rotation, while T is about translation. You'll see the difference, okay? So let's say we define a transformation matrix R, where this transformation matrix imposes a rotation of angle theta in 2 dimensions, on a point, on a vector, on things, okay? And this is a counterclockwise rotation. You know what's clockwise? How the clock goes, counterclockwise is how it goes. Okay? And the definition of this transformation matrix is this thing that you see down here. Okay? 4 elements, 2 by 2. Cosinus of theta, minus sinus of theta, sinus theta, cosinus of theta. Okay? So how do we use this transformation matrix to move a point? Okay? Let's suppose we have a point. How do we define a point in one coordinate frame? We define it as a vector with 2 coordinates. Okay? And we want to rotate it. What does it mean to rotate? I have 2 dimensions, x, y. I have my point P. Okay, it's somehow, or a vector, the same thing. Okay, I want to rotate it about the origin by an angle theta. Okay, and then at this point here, it will come, go up, and come here. Okay, and let's call this P axis. And this is called the frame 0, P0. Okay, how do I do this? I do this by multiplication. Okay, so I have my point with the 2 coordinates, and all I need to do is to multiply it with this transformation matrix that we saw, this magical 2 by 2 matrix, and the point will be moved. Okay, do you believe me? No? You shouldn't believe me. Okay, so if you don't believe me, then we should see an example and make you believe me. Okay? Let's see one example. Concrete example. Y, and then I have a point with coordinates 1. Let's make it bigger. So this is 1, 1. This is 1. This is 2. Okay, so I have a point P. This is coordinate frame 0, and this point has coordinates on coordinate frame 0, 1, and 2. Okay? So how do I write this point? Point 1 and 2, 0. And let's say I want to rotate it by 90 degrees around this axis. Okay? Do you remember how did I define the transformation matrix R? Don't remember? Makes sense? Don't worry. It's cosinus of theta minus sinus of theta, sine of theta, cosine of theta. Okay? So let's say this is R of theta. So if my theta is 90 degrees, then where do you think this point will end up? So if this rotates by 90 degrees, let's say, so this means that this will be perpendicular, same length. Where do you think it will end up? Any idea? It will end up basically, I didn't do it correctly, it's probably somewhere here. This is perpendicular. So it will end up at -2, 1. Okay, if this is 90 degrees, this theta. You can try with a paper and pen and translate it. You'll see it's going to end up there. Now let's see what the method I explained there says. Okay. If theta is 90, what is cosinus of theta? How much? Now there. 0. Don't be a saint. So this is 0. Sinus of theta, minus sinus of theta? -1. Sinus of theta? 1. And cosinus of theta? Cosinus of 90? 0. Okay? So let's practice multiplication of matrices. So R90 multiply P0, and we're going to get a P0 accent. Okay? So this is 0 minus 1, sorry, 1, 0, and this is 1, 2. So what does this give me? You remember matrix multiplication? 1, 2. What will be the result first of all? Column vector. Does it make sense? After I move a point, the result should be again a point, right? How do we define a point? As a column vector. So the result of this should be a column vector, right? Now I see a bit rusty with multiplication. So this is, what dimensions does this one have? The matrix is a 2 by 2. 2 rows, 2 columns. This one, what dimensions does it have? 2 by 1. First we talk about the rows, how many rows it has, and then how many columns. So this is a 2 by 1. Can I multiply these things together? Why? The columns of the first matrix is the same as the rows of the second matrix. This can also be a matrix. Okay? It's a vector because it's one column again. Okay? Because these two dimensions are the same. And the result will be as the rows of the first matrix and the columns of the second matrix. Okay? So it will be a 2 by 1. Okay? Now, which 2 by 1 will it be? How do I calculate it? Don't tell me the result. How do I calculate it? So everybody remembers. Sorry? What?
0 times 1 plus minus 1 times.
So the first row with the first column is the first element here. Okay, so 0 times 1, 0, plus minus 1 times 2, minus 2. Looks promising. Okay. And the second element will be the second row with the first column. So 1 times 1, 1, plus 0 times 2, 0, so 1. So it says that if I have a point with these coordinates and I apply a transformation, which is a rotation around the axis with 90 degrees in this case, I will end up with a point with these coordinates, which is what we expected as well, right? -2, 1. Okay. And this is what goes to there. Okay, I have my initial point, I apply the transformation, and I get my endpoint. And this is a better drawing than the one I have on the board. So if I start from this point, which is this point, I multiply it from the left with this transformation matrix, which is 90 degrees counterclockwise rotation. I end up with this point, right? Put. I could do it for any degree. It doesn't have to be 90. It can be 25, 30, 5, 3.3, whatever. Doesn't matter. Okay? It will result in a counterclockwise rotation around the x-axis, around the origin. Okay? Now I did this with 1 point, but I could have had 2 points. These 2 points, these 2 points. I could have had another point here called Q with coordinates to 1. Okay? I could have applied this, multiplied this with this point and this with the other point and get 2 results, or I could do it in 1 step. Okay, how do I do this? I erase this. So I can write my 2 points together as a matrix. P0 and Q0 together. Okay? What is P0? Is 1, 2, and Q0 is 2, 1. Okay? And if I apply this rotation, which we saw it was 1, 0. Okay? Can I multiply these 2 things together? Let's call this, I don't know, let's not call this. Okay, can I do this? P0, Q0. R is 2 by 2. This is 2 by 2. Can I multiply them together? I can, and the result will be a 2 by 2. Okay, because I give as input 2 points, I expect to rotate and end up again with 2 points. Okay, so the result will be a 2 by 1. Okay, I will not do the calculation here, but you can see it visualized here. If I have these 2 points, P and Q, I can group them together, I can multiply them with this transformation, and I will end up with a transformed P and Q, both by 90 degrees. Okay? And of course, this could have been 13 points. Let's say 14, because some people are superstitious. Okay? 14 points. Again, I would have a 2 by 2 multiplied by 2 by 14. The result would be a 2 by 14. So I would have 14 points transformed. Or how many are there? Okay? Now remember, points and vectors is the same thing. Okay? This could have been vectors. Points is the same notation, doesn't matter. And we'll see where I'm going. Clear? Now things are easy in 2 dimensions because I only have 1 transformation matrix, 1 transformation for rotation. Okay, because I can only rotate around here. I'm stuck on this plane, so I cannot rotate around anything else. I can only rotate here. Right? 2 dimensions, 1 rotation. 3 dimensions, how many rotations? Or let's go back. 1 dimension, how many rotations? 0. No, I cannot rotate around anything. I'm stuck on the line. Okay? If I'm 2 dimensions, I'm on a plane, I can rotate around the plane. If I'm on 3 dimensions, so from 1 dimension 0, 2 dimensions 1, 3 dimensions 3. Let's see. And then you'll tell me about 4 dimensions. Okay. So 3 dimensions. Around how many axes can I rotate? 3, right? I can rotate around 3 axes. I can rotate like this, I can rotate like this, I can rotate like this. So yeah, 4 dimensions, who knows? I don't know. If 1 is 0, 2 is 1, 3 is 3, 4 probably is, I don't know, 16, I don't know. Difficult. Good. Now in 3 dimensions, yeah, we have 3 rotations that I can have. One point can rotate around each one of the axes. Okay? Therefore I have 3 transformation matrices that I can have. Now, what do you notice about the transformation matrices in 3 dimensions compared to the one in 2 dimensions? What's different immediately? They're 3 by 3, right? For 2 dimensions, we have 2 by 2. For 3 dimensions, they're 3 by 3. For 4 dimensions, it will be 4 by 4. Okay? Great. And this is how we define the 3 transformation matrices, the 3 basic transformation matrices for the 3 basic rotations around the x-axis, around the y-axis, and around the z-axis. Here you can see rotation by arbitrarily angle theta, by an angle phi, and an angle omega. Okay? Now, what does it mean? How do we visualize rotations in 3D? You can have an idea here. As I said, x is blue, y is green, z is red. And here you can see a point rotating around the x-axis. Trying to visualize it, here you see a point rotating around the y-axis, here you see a point rotating around the z-axis. Okay? Now, what did we say about 3 dimensions? Is that these are 3 by 3, the transformation matrices. What do we say about points? A point in 3 dimensions has how many coordinates? 3 coordinates. Therefore, a point in 3 dimensions, will be a 3 by 1, right? So we can do this multiplication again. And the result will be another point space. Okay, I could do an example. Let's do a quick one. Okay. Let's say this is y, this is x, this is z, and we have a point, say some coordinates. 2, 1, 0. So let's say P is 2, 1, 0. So this means it has x2, y1, and z0. So it's here. Okay? Remember, x is getting out of the board. This point is floating somewhere here. Okay? And around which axis should we rotate? X, y, or z? Z? Z. Okay? Yes. What? Complicated? 3D or no? Okay, so we have x pointing outwards and this point here floating here basically. Okay? And we're going to rotate around z. So it's going to be a rotation around z, like this. Okay? Okay, why not? So let's say we rotate around with 90 degrees. It's usually easier. Okay? So we expect that this will rotate with 90 degrees around z. Whoop, so it's going to come somewhere here in the back. Whoop. So I expect it to be at this position here. Okay, this is again on the same plane. Let me try to visualize it. So this is x, this is the point, and it rotates and it goes in the board and behind the board. Like this. Okay? Let's quickly see. So I have point at 0, so this is 0, with coordinates 2, 1, 0. and I have a transformation around Z by 90 degrees. Right? Which transformation do I care about? Which matrix? The last one, because it's a rotation around Z. Okay? Now, if Z is 90, what is this? What is cosinus of 90? 0. Sinus of 9 minus sinus of 90 is minus 1. 0, 1, 0, 0, 0, 0, 1. Right? Good. Let's multiply this with this. So P, the transformed one, will be equal to R Z90 P 0. So let's see, 1, 0, minus 1, 0, 1, 0, 0, 0, 0, 1, with 2, 1, 0. Now this is a 3 by 3, this is a 3 by 1, the result will be a 3 by 1 point. What is the first element? This by this, minus 1, this by this, 2, and this by this, 0. So basically it has coordinates x minus 1, so minus 1 in the minus direction of x, y is 2, and z is z. You see how it rotates in the back. Could have done a rotation around y or a rotation around x. Okay? I need to use my body for science. Good. Now we just talked about rotations. That's one type of basic transformation when we rotate stuff, but we can also translate stuff. So I might have a point that I'm rotating around an axis, okay, but it might also just translate along an axis. So it might translate along this direction, or in this direction, or in this direction, okay, no rotation, just translation. Therefore we need to extend a bit, because this is just for rotation, not for translation. And we define another type of matrix, transformation matrix again, which is called homogeneous, which contains, part of it is about the translation, about the rotation, and part of it is about the translation. Okay? Now, I'm not sure if this is super clear, but basically this big homogeneous transformation matrix, we usually write it with T, it has parts. It has, as I said, a part which is the rotation. If you remember, the rotation matrices were all 3 by 3. Okay, so this, in that position, we have a 3 by 3 matrix. Here we have one row with 3 elements, so 1 by 3. Here we have a 3 by 1, so 3 rows and 1 column. Okay, and this part relates to the translation. And here we have a 1 by 1 element, so 1 element. Now what's the case is that this line here, the 1 by 3, is always zeros. So 0, 0, 0. And this element here is always 1. That's how we define stuff. Okay? And this 3 by 3 is the rotation, so how much the object rotated around an axis. And this 3 by 1 shows us how much it translated around an axis. Okay? Now we have 3 axes, and here we have 3 elements. So you expect that these 3 elements are all each for one axis. Okay? And that's how it is. Basically, let's forget a bit the rotation. Maybe one thing to notice about the transformation. What happens if the rotation is 0 in each one of these? What is this matrix here? This will be 1, this will be 0, 0, 1. So this will be the identity. If this is f phi 0, this will be again the identity, right? And if omega is 0, this will be again the identity. And it makes sense. If I don't have any rotation around x, it is the same as if I didn't have any rotation around z as well. Or okay? So if this part is the rotation and we have no rotation, then this part will be the identity matrix. Okay? So for homogeneous transformations, if I have just translation, no rotation, okay, here you see is the identity matrix. And then if I have translation on x-axis, I have some element, some value here on the first element, and 0, 0 in the other two. If I have translation on the y-axis, it's the second element. If I have translation on the z-axis, is the third element. Okay? So this means if I'm moving, if my point moves along the x-axis, the first element will have some value equal to the distance that it translated. If it's moving on the y-axis, or if it's moving on the z-axis. Okay, no rotation here. Clear? Okay, we'll see. Then, if I have no translation and only rotation, then I have something very similar to what we already saw. Okay? You remember these three matrices that we saw earlier? They fit in here, and the translation part is 0, 0, 0. Okay? Yes?
And we have two translations at once.
We can. And we can have 5 rotations and 3 translations and then 1 more rotation at once. And we'll see it in 2 slides how. Yes. You mean combining and putting here A and B at the same time, right? You can, but you're not allowed yet. In 3 slides, you will see how nice mathematics are. Okay? Good. So these 3 are basically these 3 with 1 extra row and column where the translation is all 0. Yeah? Now, what problem do we have here? Here we had the rotation as a 3 by 3 matrix, and the point was a 3 by 1 matrix or vector, or how you want to call it. And I could do this multiplication, right? But if this one becomes 4 by 4, how can I multiply a point? I cannot, right? So we cheat a bit, and for each point in 3 dimensions, we add 1 extra element. So this becomes a 4 by 1. And this extra element is always equal to 1. Okay? So this will be a 4 by 1. Okay? This will be. Okay? So in 3 dimensions, points are defined by 4 elements, out of which the last one is always 1, so it doesn't really count, but it helps us do this multiplication. It's a mathematical thing. I don't understand it 100% either. How come they thought about this, but it works. And we're engineers and we care about stuff that works, not about. I'm not a mathematician. Okay? And it works very good. Okay, great. So, if I want to do a translation or a transformation, let's make a very quick example with translation as well. Let's say I have the same point here, okay, and I want to do a translation. Okay, no rotation this time. I want to translate around which axis? Say an axis, around Z axis, so it goes up by a distance of 3. Okay? So what will be the new coordinates of this point? So point 2, 1, 0. If I push along the Z direction by 3, 2, 1, 3. Yes. 2, 1, 3 is the expected result. So I expect it to be 2, 1, 3. Let's see. So the translation around Z by 3, which matrix is it? It will be a matrix that looks like this, right? 3, correct? Correct? Okay, so let's multiply these two together. I'll just write it here to save space. 2, 1, 0, 1. So this magic one that we add. Let's see, what's the result? This is a 4 by 4. This is a 4 by 1. So we can do the multiplication. So help me a bit. So this is 1 times 2 plus 0 times this, 0 times this, 0 times this will be 0. So this will be 2. Right? This one, the second element is this times this. 0 times 2, 0. 1 times 1, 1. Plus 0 times 0 plus 0 times 1, 1. Right? Third element is 0 times 2, 0, 0 times 1, 0, 1 times 0, 0, plus 3 times 1, 3, and this will be 1. So what are the coordinates of the point after we apply this transformation? What we expect. Okay? Is it clear to everybody? Now, we talk about points, but we saw that points and vectors is the same thing, right? Okay? And we saw that a coordinate frame is a collection of 3 vectors. Okay, so a collection of 3 points, or anyway, a 3 by 3 matrix. Or if we use this new notation, it will be a 4 by 4, because each point is a 4. Okay? So basically, if I have a coordinate frame, a base coordinate frame with a thin line, okay, and then another coordinate frame that is going to be moving around with the thick lines, and they are totally aligned, then I can express this coordinate. Let's maybe with the board as well. So I have one coordinate frame called 0. Okay. Then I need, yeah. Okay, so this is 0. And then I have, this is supposed to be green, but it's not. So V1 on 0, V2 on 0, and V3 on 0. Okay? If these V1, V2, V3, they are unit vectors, let's see. V10 will be, what coordinates will it have? So it will be 1, 0, 0, right? 1, 0, 0, and I add one more. No, actually, this one. No, forget it. 1, 0, 0, and this will be 0, 1, 0, and this will be 0, 0, 1. Okay? So if I put them together, that basically shows me the orientation of the vector, of the coordinate frame, and it's this part here, the first 3 by 3. Okay? And this other part shows me basically how is the origin of this new frame expressed on the base coordinate frame. Okay? Anyway, the idea is that I can write this 4 by 4 matrix expressing the green coordinate frame or the thick lines there as expressed on the base coordinate frame, so the white coordinate frame or the thin lines there. Okay? And it's this identity matrix 4 by 4. Now, can I move it around? And how do I move it around? How do you think I can move this vector, this coordinate frame around? Let's say I want to rotate it. What should I do to it? How should I rotate? What do you think? Say for some reason I want to rotate it around the axis of x. And I want it to look like I have this. And I want it to look like what we saw there earlier. So rotated by angle theta. How can I do this? What do you think? Multiply with F? Cannot hear you, sorry. With that matrix, the transformation matrix, right? Okay, so as we saw, if we multiply a point with a transformation matrix, it gets transformed, either translated or rotated. I can do it with 2 points, you saw the example. I can do it with 3 points on 3 vectors, right? So I can take this identity matrix and I can multiply from the left with one transformation. In this case, it will be a rotation around x, if this is x. Okay? And we'll rotate like this. And you see also in the picture, the x remains the same, it just rotates by an angle theta. Okay? This is theta. Okay? You remember there we discovered that the new coordinate frame has it was like this. If you check your notes, I think so. Right? And we translated it with 45 degrees. We rotated it with 45 degrees around x. Okay? So we started with the identity matrix. Let's say 1, 1, 1. Okay, this was the initial thing, and then if I multiply this with on x by 45 degrees, I should expect to get that thing again. Okay, let's see what is this. So on the left side, what is the transformation around x by 45 degrees? It's 1, 0, 0, 0. Cosinus of 45, 1 over square root of 2, I think, or 2, yeah. Minus sinus of theta is minus 1 over square root of 2, 0, 1, right? And if this gets multiplied with the unit and the identity matrix, what will happen? It will give me the same thing as the beginning. Okay? So there we saw already like an example of transforming coordinate frames. Of course, now we have this 4 by 4 notation, so normally I should write this as like this. 1, 0, 0, 0, and 0, 0, 0, 1, 0, 0, 0, and this will be 0, 0, 0, 1, 0, 0, whatever. It's the same. Okay? So that's how I can apply the same transformation matrix that we saw for coordinate frames, not just for points. Okay? Now, what if I want to do another transformation on this frame, on the already transformed one? How can I do it? So I rotate it on x by theta. Let's say I want to rotate on y by phi. After I rotate it on x by theta. How should I do it?
So after we rotated it once, we rotated from this point onward, like
Yeah. So now I had this frame. I applied this transformation and I got this frame. And I want this one to move it again.
we take the axis that moved the transformation from a specific
Exactly. So I can start different transformations one after the other. Now, you see here I have this frame and I multiplied from the left with this transformation, okay? So the next one, I should multiply again from the left, the result. Okay? So this is how I can chain different transformations. Okay, I can have an initial set of vectors v0, let's say, I transform it by a rotation on x by theta by multiplying from the left, and the result of that, I multiply again from the left with another thing, with another transformation. Okay, but which one happened first? You have to be careful, and that's something you make often mistake with. It's not that I first rotated around y by phi and then by x on x by theta. Okay, I don't read from left to right. But you remember, I first did. Cannot really focus. I first do this multiplication, like here, and then the result I multiply from the left to this. So basically, I first rotate around x, and then I rotate around y. So I read from right to left. So if I tell you first translate around z, and then around y, and then around x, you should do like first I rotate around x by theta, then I rotate around y by phi, then I rotate around z by, I don't know, omega. Okay? First, second, third. Clear? Good. Now, what is the result of these two, let's say? This is a 4x4, right? And this is another 4x4. So the result is, it's a 4x4. Okay. So again, I could say that this is one transformation, one composite transformation that is composed of two basic transformations. Okay. So this will have some numbers there that will be as if I first multiplied from the left with this one and then by this one. Okay. So that's what I'm writing here, that basically any transformation from one frame to another can be broken down to simpler transformations around the basic axis. Okay? And the inverse. Simple transformation around the basic axis can be composed into another transformation around, more complex one. Okay? Now, why do I insist so much on this happening first and this later on? Why don't we write, is this the same thing, basically, as the one above? Are these two equal? Matrix multiplication is not commutable. We cannot change. Sometimes we can, but sometimes we cannot. Okay? Good. Let's hurry up because we're running out of time. Let's answer the question from the back. He said that can we put two translations at the same time? Let's say I have translation on x by, I don't know, alpha. Okay? And then another translation on z by beta. Okay? This is just translation. Okay, not let's write translation. Okay. So what form does this one have? You remember? Translation on z by beta will be basically this thing on z, and on x will be this thing. Okay? So what will be the result of these two first translating on z by beta, and then on x by alpha. So I first move up and then on x by alpha. Should be, can you do the multiplication fast? First row, first column, 1, first row, first column, 0, 0. Basically this will be this. Okay, let's focus on the last column because it's faster. So the last column will be, how do I figure out? What's the first element? The first row with the last column. It will be alpha. Second element will be the second row with the last column, will be 0. And the third element will be the third row with the last column, which will be that. So this is what you were saying, right? Combine A and translation on X and zeta in one matrix. You can do it only now that I showed you why. Now that you're experienced, you leveled up. But basically the reason is because these multiplications result in this thing always. Okay. Now if I do the inverse, it's going to be the same. Yes? We said that it's not commutable.
We said that it's not always.
Yes. Okay. Good. Smart people. So it's the same thing if I translate on x and then on z, then it's the same as translating on z and then on x. So it will give me the same result. But it's not with rotations. Like it's not the same if I rotate around z and then around x. I'm not going to end up in the same point if I rotate around x and then around z. I don't know. Whatever. You can try things out. Like it's usually like this. If I first rotate my hand like this and then like this, it's not the same if I rotate like this and then like this. Sometimes it works, sometimes it doesn't. How do rotations look like? This is how rotations look like more or less around x, around y, around z. Okay. And now one final thing, which is going to trouble you a lot probably during the semester, but we have to clear it out, is I keep on saying that we multiply from the left, right? I have a matrix V and I multiply transformation from the left. Why from the left and not from the right? If this is a 4x4 and this is a 4x4 because this is a coordinate frame, I could do it from the right as well, right? Or from the left. Does it make a difference? We said it's not commutable. Now, we can do both, but the representation is different. Okay? If I multiply from the left, now what do we see here? I have a fixed coordinate frame, 0, okay, and I have another coordinate frame that is expressed on 0. So V subscript 0, okay. And here what do we see? If I multiply from the left for a rotation around x by theta, here you see like different theta, just so you see it moving, okay, it rotates around which x? This fixed x, right? You see? Rotating around this point, around this axis. Is it clear? Now I can multiply from the right, but it will have a different meaning. If I multiply from the right, my coordinate frame will rotate around its own x-axis. So you see here now it doesn't rotate around this axis, it rotates around this axis. Do you see it? Okay, see them next to each other. Multiplication from the left, the same transformation matrix, right? Rotation on x by theta. And multiplication from the right. They both have a meaning, but it's a different thing that happens to the coordinate frame. Okay, multiplication from the right. Now, what's important to understand is that this coordinate frame, expressed by this V0, is expressed on the fixed frame. Okay? What does that mean? It means that I have a fixed frame, I had some vectors, I don't know however they look like, and the coordinates here were the coordinates on this frame, on the fixed frame. Okay, that's what it means. V is expressed on 0. What we said in the beginning of the lecture. Okay? Now, if I multiply from the left, it will rotate around the axis, or it will transform anyway, not just rotation, translation is the same. It will transform around the axis of the fixed frame, the frame that the movable frame is expressed in. If we multiply from the right, it will transform around its own axis. Okay? Very basic. Make sure you check the animations also at home tomorrow on videos. Okay? And as I said, this is not just for rotations, it's the same for translations. Okay? So here you see I apply translation on x by a distance delta on this frame. You see now it translates along this axis, parallel to the x-axis of the fixed frame, while here it translates around its own axis. Okay? All clear? We will have to come back to this again and again. It's mind-blowing a bit. It took me as well quite some years to figure it out. But we're gonna keep on touching about this little detail again and again. And it all comes back to where am I expressing the coordinate frame in? Okay, which frame? Now, one last thing that we need to see, and then we have all the background we need, is how we switch frames, how we go from one frame to another. Okay? This is important in robotics specifically, because you might have, for instance, a robot, and it has a sensor on one part of the robot and another sensor on the other part of the robot, and then this sensor tells you, I have an object in position, I don't know what, coordinates what, and this needs to know, okay, in my frame, where is that point? Okay, so I might have, I don't know, one frame here on one sensor, for instance, and another frame here on the base of the robot, whatever, and I have a point where that this guy knows where it is, and I need to tell what coordinates does it have on another frame. Okay? Again, concrete example, let's say I have a camera on the robot, it detects an object, but the camera is not in the same frame as the robot, I don't know, and then the robot needs to know how to move to go to that point, or something like this. Okay? How do we do this? Very basic. If I have a point if I know the coordinates of a point in one coordinate frame, let's say I know I have coordinate frame 0 and I have coordinate frame 1, okay, and I know the coordinates of one point in one frame, okay, something like this. Let's say I know point 1, P1. How do I figure out what are the coordinates of this point in this coordinate frame? So how do I figure out P0? Basically, I need to know what kind of transformations did I need to do to go from this frame to this frame. Okay? I'm jumping a bit some things here, but you will practice more in the labs on this. The idea is that you can imagine that this frame was here, and I had to apply, I don't know, translation, rotation, 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 I need to go here. So I have like a series of translations, rotations, translations, rotations, which, what's the result of this? What will be the size? It will be another 4x4, so another complicated transformation, a composite transformation that shows me how did I go from 0 to 1. What kind of transformation did I do go from 0 to 1? Okay? And then this is how we symbolize this. What transformation did I need to get in order to go from 0 to 1, from here to here? Okay, and I just need to multiply the point, and I get the point in this plane. Again, you will practice this in the lab. The first lab is about this, I think. But yeah, we don't have much time left. Do you have questions?
What's on the last slide?
What's on the last slide? Good question. More questions? Yes?
So can we have also rotations and translations at the same time?
What do you mean at the same time?
Like in the translation matrix, we also put the seeing cos, minus things and creating.
So coming up with something like this. You can, but you have to be careful. Can you please be quiet? You can start talking if you want, but be quiet. Don't shout. So you can, but you have to be careful. Why? Because you have to think again what happens first. Do I first translate and then rotate? Or do I first rotate and then translate? And you will end up in a different position if you first translate and then rotate, or if you first rotate and then translate. Let me try to give you an example to convince you. Let's say I have a point here, okay? And let's say I do a translation on Y by D, and then a rotation on X by theta, okay? If I first translate and then rotate, I will end up, let's say, here. Okay. If I first rotate and then translate, I will end up somewhere else. I might end up at the same point based on how much I translate or rotate, but that will be like by accident. Okay. So if you write something like this, let's say I do a rotation around. Let's take this example. Rotation around X, 0, 0, 0, 0, 1, 0, 0, 0. And then this is cos theta minus sine theta, cos theta. And then you're saying, okay, I want to rotate and translate at the same time. So I want to translate on here as well, right? That's what you're saying. This will be, I think it's first rotation and then translation. You will get this result if you take the rotation matrix and then multiply from the left the translation thing. I'm not sure, I have to think about it. Or the other way around. So yeah, if that's what you want, you can write it like this, but make sure this is what you want. So it's safer if you just do it step by step. More so because we're going to do everything in MATLAB, a computer, so you don't, write things by hand anyway. But by experience, you will get to write things maybe like this. But be careful, okay? That you're doing what you want. Okay? Any more questions?